Hello everybody, welcome to lecture 23 of this course. So, today we are going to start by looking at some more examples of push-down automata. Then we will try and explore the connection between context-free grammars and push-down automata. In other words, we will see that if you look at the class of languages accepted by push-down automata versus the class of languages accepted by context-free grammars, what are the relation between these two classes. So, let us start by looking at the following example. So, our first example is going to be a language, let us call it L1. So, it has strings over the alphabet ABC of the form a to the power I, b to the power j, c to the power k, such that either I equals j or j lies between k and 2k. Okay. So, if either number of a's or b's are equal, we will accept this string, or if the number of b's lies between k and 2k, where k is the number of c's, even then we will accept such a string. Okay. So, how do we use how do we construct a PDA for this language? So, the idea is that, so because we have a OR over here, we will use epsilon transitions, we will use non-determinism in the form of epsilon transition to branch off at the very beginning. So, even before I start reading the first symbol of the string, I branch off into two paths, into two branches, where one will check whether the number of i's, the number of a's is equal to the number of b's, that is I equal to j or not, and in the other branch I will check whether j lies between k and 2k or not. Okay. So, I am going to non-deterministically decide to do one of the two things and branch off accordingly. So, let us see. So, we have a start state. So, from my start state on, without reading anything and without changing the stack. Okay. So, the only thing that I will do is that I will add a marker at the bottom of the stack. So, I will add a hash symbol at the bottom of the stack, and I will do the same thing here as well. Okay. So, I go to these two states. So, in this state I will check whether I is equal to j, and from this state I will check whether j lies between k and 2k. So, how do I check whether I is equal to j? For every small a that I see, I will pop in some symbol, I will push some symbol onto the stack, and for every b I will pop it out, and in the end I will compare. Okay. So, every time I see a, let us say I push in a onto the stack, then I move to another stack without move to another state without changing the stack. Here, for every b that I see, I will pop out an a. Okay. And now, at the end of seeing all the a's and b's, if I have only the symbol hash on the stack, I know that I is equal to j. So, if I have hash on top of the stack, I will just remove it. I know that I is equal to j, and on this state I will just see an arbitrary number of c's. Okay. So, if I see a c, I do not do anything to the stack, it does not matter what I do, and finally, at the end of seeing all the c's, I will just go to a accept state. So, this portion of my push down automata accepts languages of the form or strings of the form a to the power I, b to the power j, where I is equal to j, and c to the power k. Now, I am going to accept strings of the form where j lies between k and 2k. So, first I am going to see an arbitrary number of a's, because I is irrelevant here. So, I do something like this. So, on seeing an a, I do not disturb the stack. Now, I have to check this. So, what is the idea here? How do we check whether the number of b's is between k and 2k? So, the idea is we will again use non-determinism over here. What we will do is that every time I encounter a b, I will push a symbol onto the stack. Okay. So, find is equal to j on the stack, because that is the number of b's. Now, when I encounter a c, either I will pop out a single b or I will pop out 2 b's. Okay. So, for example, if the number of b's is exactly twice the number of c's, that is j is equal to 2k, then for every c that I see, I need to pop out 2 b's, right. On the other hand, if k is equal to j, then I need to pop out 1. So, I will non-deterministically decide which one to do, whether to pop off a single element from the stack on seeing a c, or whether to pop off 2 elements from the stack on seeing a c, okay. And this I keep on doing. So, when I see okay. So, basically from here I go to another state where first what I do is that on seeing a b, I push in a symbol, let us say capital B, onto the stack. Now, I go to another state, okay, and from this state I will do one of two things. So, either on seeing a C, I pop out a B, or on seeing a single C, I will pop out 2 B's. So, to do that I will use another additional state. So, first on seeing a C, I will pop out a B, which takes me to this state, and from this state I will pop out another B without reading any symbol, that is epsilon. So, these two operations together correspond to popping out 2 B's on a single C, which takes me back to this state. So, observe that I non-deterministically do one of the two things in this state, either this or this operation. And now finally, when all the C's are popped out, I will just go to this state if the symbol on the stack is the hash symbol. Okay, I will pop it out and I will go to the accept state. Okay. So, this is the automata. So, once again we are using non-determinism in two places. First, we use non-determinism to decide which of the two tests we are going to perform. Second, if we are going to do the second check, that is j lies between k and 2k, we use non-determinism to either pop out a single b on seeing a c or pop out 2 b's on seeing a c. Okay. So, these are the two things and the rest is pretty self-explanatory. So, let us look at our second example. So, recall the definition of reverse of a string. Okay. So, we have this language L2, which is also sometimes called the palindrome. So, this consists of all strings W over, let us say, AB star, such that W equals reverse of W. Okay. So, strings which read the same no matter which side I read it from left or from right. Okay. So, how do we accept a string of this form using a pushdown automata? So, the idea is we will again use non-determinism over here, and we will use non-determinism to kind of figure out what is the middle point of the string. Okay. So, what we do is that I start scanning the string from the left hand side, okay, and whenever I scan the string, I keep on pushing the symbols that I have read onto the stack. Okay. For example, let us say that I have a string A, B, A, B, let us say A, B, A, B, B, and then we have B, A. Okay. So, first what I do is that, so this is kind of the middle point of the string. So, till the middle point I will keep on pushing symbols onto the stack. So, first I push E, okay. I kind of skip the middle point if it is if it has odd length, and if it has even length I will just push the middle point as well, and then I compare with the rest. For the remaining part of the string, if since I have a B here, I will pop out this B, and then I have an A here, so I will pop out this A and I will accept. Okay, so I will check the first part of the string with the second part of the string with the help of my stack. Okay, and I have to carefully handle the case when it is odd or when it is even, the length of the string. So, here is the automata. So, first on my start state I will push a symbol hash onto the stack once again to check whether I have reached the end of the stack at any point or not. Now, from this state, okay, so this is the state which will correspond to my push operation. So, if I see a A, I will push a capital A onto the stack, okay, and if I see a B, I will push a capital B onto the stack. Okay, so it's the same on the same transition. So, if I see a I will keep on pushing capital A, if I see B, I will keep on pushing capital B. Now, I have to go to a pops state. Okay, so this state corresponds to, so let me call it Q push, and this will be Q pop. Okay, so in this state, if I see a A, I will pop out an A, and if I see a B, I will pop out a B, and now I check whether the top of the stack is hash or not. So, without reading anything, if hash is the symbol on the stack, I will just remove it and accept. Okay. And how do I go from Q push to Q pop? Okay. So, this is where I will use non-determinism. So, either the string has even length, if the string has even length, then basically without reading any symbol, I go from Q push to Q pop even without changing the stack, okay, because the first part and the second part are the same. On the other hand, what can happen is maybe the string has odd length. For example, when this is the case, if the string has odd length, I do not change the stack for the middle symbol. Okay. So, when I get the middle symbol, I do not change the stack, I just read that symbol and proceed. So, if the middle symbol is a, I read A without changing the stack. Similarly, if the middle symbol is a B, I read B without changing the stack. Okay. And this is the push down automata. So, the crucial point is that at this state we are making use of the fact that we are making use of non-determinism to find out what is the middle point of the string, because if I have reached the middle point, then I need to go to Q pop. If I have not reached the middle point, I need to stay at Q push. That is what the automaton does in a non-deterministic manner. Okay. So, we have this example. So, now we are going to look at the other aspect of today's lecture, that is the relation between context free grammars and push down automata. Okay. So, how do these two computing objects compare in their power? So, as it turns out that these two computing objects, they are equivalent in power, in their expressive power. Okay. Although they have a very different structure, one has an automaton structure, the other is a grammar, but the class of languages accepted by context free grammars is exactly equal to the class of languages accepted by push down automata. Okay. And that is what we are going to show in the next part. I am not going to go through the complete proof in detail, but I am going to give a idea as to how the proof essentially works. Okay. So, let me state this as a theorem. So, L is a context free language if and only if there exists a push down automaton P such that L equals L of P. So, recall that context free languages are exactly those languages which are accepted by context free grammars. So, what we are saying is that if a language is a context free language, that is if there is a context free grammar for a certain language, then there is a push down automata which accepts it, and if there is a push down automata that accepts a language, then it is a context free language, which means that there is a grammar for it. Okay. So, we are going to see both the directions here. So, I am just going to write this as proof idea. So, let us see why the first direction, that is context free grammars are a subset of push down automata. Suppose if we have a context free grammar, how do we create a push down automaton out of it? So, the idea is the following. So, what you do is that you take a context free grammar and you use the stack to store the current string on the stack. Okay. So, we start with the start variable s, then we replace the start variable with some rule for s, okay, and then we get some other string over variables and terminals. Then maybe I replace some other variable on this string to get another string. Okay. So, these strings are called sentential string. So, I keep on getting these sequence of sentential strings. Okay. So, if you recall the definition as to how a context free grammar accepts a string, it is basically a string is accepted by a context free grammar if there is a sequence of these sentential strings, these strings over terminals and variables, such that one string can be derived from the previous string by replacing a single variable with its production rule, and the last string is essentially just a string over terminals. So, what we do is that we use the stack of the push down automata to remember all these sentential strings, okay, and we keep on doing it, and whenever I have and basically the way I put it on the stack is that I put it in a top down fashion. Okay. So, the left portion of the string stays at the top of the stack. Okay. So, whenever I have terminals on this string, I will match them off with input symbols, and then when I have a variable, I non-deterministically choose some rule of the variable to replace that variable with that rule. Okay. So, let me write it down to give a little better idea. So, use the stack of the pushdown automaton to store the intermediate strings generated over sigma union V star. Okay. So, as I said, these strings are also called sentential string. So, we use the stack of the PDA to store this. How do we start? We start by pushing S onto the stack. Okay. So, S is our start variable. I push S onto the stack and we do this. The left of the string is at the top of the stack. Okay. We match off terminals by input symbols. Okay. So, we create a transition function that will basically match off terminal symbols on the stack with input symbols and pop them out. Okay. So, basically match off means that if I have a terminal symbol, let us say small a at the top of the stack, I will essentially read a small a from my input and pop off this small a from the stack. That is what it means to match off. Okay. And we replace a variable non-deterministically with one of its production rules. Okay. So, to motivate this, let us just look at a quick example. Okay. So, I am not going to give the entire example, but just a part of it. So, suppose we are looking at the grammar for 0 to the power n, 1 to the power n. So, we have the rule s going to 0 s 1 and s going to epsilon. Okay. So, what we do is that, so essentially if I have, let us say I have generated at some point a string of the form 0 0 s 1 1. Okay. So, from s I first generate 0 s 1, then I generate this. So, at this point basically my stack, so what does it contain? So, initially I start with, s on the stack. Now, since the top variable of the stack is a variable, since the top symbol of the stack is a variable, I replace s with its production rule 0 s 1. Okay. So, I have 0, I have s and I have 1. I push these 3 symbols onto the stack. Now, I try to find what is the topmost variable on the stack, and to do this I will match off strings basically. So, let us say my input is something like 0 0 1 1. So, I match off this 0 with this 0. Now, I have a variable on the top of my stack. So, I replace S with its production rule 0 0 S1. So, I have 1 here and I replace S with 0 S1. So, I get 0 S1. Okay. Once again I match off this 0 with this 0. Again I have a variable at the top of my stack. So, I will replace S with its production rule epsilon, okay, and therefore, I get 1 and 1 on the stack. Now, I match off 1 with 1 and I match off this one with this one. So, now the input is completely read and the stack has again become empty. So, this gets accepted. So, that is how it works. Okay. So, for the other direction, we have to show that PDAs contain context free grammar. Okay. So, here without loss of generality, we assume the following. So, first we assume that the PDA has a single accept state. Okay. We next assume that PDA has empty stack when it accepts, and thirdly we assume that it either pops or pushes in every step, okay, but not both. Okay, so, this is an exclusive OR. So, how can we ensure this? If the PDA has multiple accept states, I just put epsilon transition from all these accept state to one accept state. If the PDA, when it accepts, it does not empty out its stack, what we do is that if it reaches the accept state and it has exhausted the input, we will create a new accept state, and before going to the new accept state, we will pop out everything out of the stack, we will make sure it is empty, and then non-deterministically move to the new accept state once it has become empty. To ensure that it either pushes or pops in every step, but not both. So, suppose it pushes as well as pops, we just divide this transition into 2 separate transitions, where in one step it pushes and in the next step it pops, or vice versa. Okay. So, now that we have these conditions, what we do is that we create variables of the form. Okay. So, for all p comma q of the PDA, create variables of the form A P Q. Okay. So, A P Q will accept every string. So, sorry, or A P Q will generate all strings. So, I will just write it as A P Q is set of all strings that take the PDA from state P on empty stack to state Q on empty stack. Okay. So, once we have this, we will just now need to divide into two cases. So, case 1 is so let us say from going from state P to state Q, first symbol pushed is same as last symbol popped on the stack. Okay. So, if I look at the stack, the first symbol pushed is the same as the last symbol popped. So, in this case we add a rule of the form A P Q goes to small a R S B, okay, where this is the first input symbol that is read from going from P. This is the next state that we go to when going from P to the next state. S is the state from where we go to Q, and B is the last input symbol that is read when going from S to Q. Okay. This is case 1, and case 2 is when this does not happen. Okay. So, the first symbol pushed is not the same as the last symbol read. So, there is some other state in between when this the first symbol pushed gets popped out. Okay. So, in this case we will add the rule A P Q goes to A P R concatenated with A R S, where R is the state where the stack becomes empty after P. Okay. So, this is the position where it becomes empty, because it needs to become empty at some point, because the two symbols are not the same. Okay. So, I will stop here and we will continue next time. Thank you.